face. This is the water face. So the reinforcement is T12 at 110 vertical. Okay, T12 at 110 vertical. And then outside we have T10. It's T10 at 110 vertical. Okay. All right. Sometimes we will say T10 near face, and then you want a far face. Okay. All right. So, so this is the vertical reinforcement. Okay. Then, as I say, vertical reinforcement is like this. So normally, let's say this is the base. This is the base here. Okay. Normally, we will have a construction joint here. Normally, we construct the base first. So this is a construction joint. So when we have a construction joint, normally what we have is we have the starter bar. Comes in like that to land with the vertical one. Understand? Yeah. Then we have the outside face, which is this. Same thing. We have this and like that. Okay. All right. Then we will have the horizontal reinforcement. Horizontal reinforcement, and we have this horizontal reinforcement like this, and like that. Okay, so that is the complete design of the wall. Okay, so what else? Okay, the water tank normally it's sometimes from here to here might be 3 or 4 meters, okay? And then this could be very long. This could extend to 15, 20 meters, okay? So as such, most of the time you won't cast the entire wall in one shot. So most likely we have construction joint, okay? So we have construction joint. So and the type of construction joint will affect your horizontal reinforcement, because your horizontal reinforcement is basically used to control cracking. Okay, control cracking. So let's look at first before we go into horizontal reinforcement. Let's look at the joints. The joints of the wall. In the book here, they talk about the joints, construction joints. Okay. In chapter 11.2, joints in water retaining structures. Okay. If you look at the code also has one chapter, one section that talks about the joints in water retaining structures. Okay. First thing is the construction joints. So here I do joints, water retaining structure. First is construction joint. So construction joint, I mean, it appears in normal construction also, right? Let's say you have a slab and a beam. You know the beam can have 6 or 7 spans. So you're not going to cast the 6 or 7 spans in one shot. Normally you cast, you have the joints, okay? So, okay, let me ask you, let me ask you, let's say I have just talk about beams, the columns, right? Let's say I have the columns here, let's say, so forth. 1, 2, 3, 4, 5, 6, 7, 8, that's it. Let's say I have 8 span, 1, 2, 3, 4, 5, 6, 7, 8 span, right? So if I were to do it, I will have, I'm not going to cast from here to here in one shot, so I may stop somewhere, right? So where do you think they will put the construction job? Where do you think they will put the construction job? Have you encountered this problem before? Do you encounter this problem before? Anyone has any idea? This is very practical. Okay, whether you work for the site, normally you have to determine where do I stop. Huh? One third. Why one third? You may have dealt with this problem before. Have you? Huh? Have you dealt with this problem before? No. Okay. If the contractors propose here in the middle, right? So what do? You approve or not approve? You're an engineer. I'm a contractor. Right? So I say, okay, I stop here. Okay. So you approve or not approve? Is that the best place to stop? So you would probably say, okay, why don't you, instead of drawing here, maybe you do here. Okay, one third, right? One third, right? Sometimes 1/4. Okay. Now, why? Where do you get the 1/3 idea? Somebody told you or what?
I learned from them.
You learn from them. Who are them?
Internship.
Huh?
Internship.
Or internship? Or you work in a contractor?
Yes.
Okay. So you either do 1/3 here or 1/3 here, right? Alright. So why 1/3? You never ask. Huh? Okay. Because the 1/3 is a place where you neither have a maximum moment or maximum shear. Because you don't want the joint at the maximum moment as well as at the maximum shear. Okay? Because your moment diagram is going to be like this. Right? So 1/3 here, that means your moment is almost 0. Okay? 1/2 here, you have the maximum moment. Okay? And then your shear diagram is like this. Your maximum is here, right? Middle here is 0, right? But my middle here, my maximum is the maximum. So if I take 1/3, I have a little bit of shear, but my moment is 0. So that is the reason they will take 1/3 or 2/3. Okay? And what do you have? That means let's say if this is the beam here, this is a beam here. So what they will do is they will stop here. And then you have to have starter bar coming out, right? This starter bar, right? And then after that you have to lap it. Lap. Okay? Because you cannot just have the construction like that. Join like that. You cannot just have the construction join like this. Okay? You cannot say, okay, my it stop here, my rebar also stop there, right? Then I say, so there is no continuity of the rebar. So to provide continuity for rebar, what you have is, you have, let's say this is the face, and then you have the rebar coming out, okay? And then you have to, when you cast the next cast, you provide a lapping bars to continuous, right? Now you understand, right? Okay. Sometimes you should ask, not just accept, oh, you have been doing like this. You understand what I'm saying? Maybe they also cannot tell you why, because they, like you, also learning from somebody else without giving you the reason. Okay? Alright. Okay, this issue actually, I think, is addressed in the code. Okay? The code has several sections, and one section is they talk about the construction practice, the workmanship, and things like that. And then normally the construction joint, okay, here is the construction joint. In order for, before you continue, so you have the rebar actually sticking out. Okay, all right. Now, before you continue, you have to do some surface preparation. Are you aware of that? Probably not. But the consultant, I get it. You have to basically clean up. Because why? This surface here, you have cement paste, dry cement paste, right? And you may have dirt, you may have some oil, because later on you take out the formwork, you'll be exposed. You'll be exposed. So before you continue concreting, you have to use the, sometimes they use the water blast to just clean up the dry cement paste, and then you expose the aggregates. Okay, and then when you cast it, the fresh cement paste is going to bond with the aggregates. If not, you see, you have these aggregates and then you have this dry cement paste, okay, cover it, then the bonding is not very good. Okay, so normally in the construction joint they will have this kind of treatment like that. Normally this kind of things should be written in the spec, the specifications. Okay, so this is the challenge. Okay, so here, so we kind of divert a little bit because the construction joint. So this is the construction joint, and then you also have, so this is a construction joint. Okay, prepared surface. You see, why do they say why prepared surface? That means when you want to cast the next cast, you have to prepare this surface first. You don't want the dirt, you don't want any oil. Okay, all right, because the dirt will prevent proper bonding. Okay, all right. Okay, and construction procedure for walls. Okay, here you can see construction joint. The first pour, continuous, okay, alternate bay construction. First pour, second pour, third pour. This one is continuous. First pour, second pour, third pour. Okay. Now, this is alternate bay. This is construction bay. Okay. Now, why do they want to do alternate bay? Why do do one? As a contractors, they will prefer this one. Right? You want to do continuous. You don't want to do 135, then come back and do 246. These 135, 246. This one is actually to control the cracks due to temperature and shrinkage. Because after you pour this one, right? So when it shrink, there is no restraint. Understand? There is no restraint because here is empty, here is empty, here is empty. Okay? So When you do not have any restraint, then you do not have the shrinkage crack. Okay, the shrinkage crack is because you have restraint. Okay. For example, let's say a wall. Say a wall, right? When it shrink, right? When it shrink, where do you think the crack is going to occur? Is it, first of all, is it a horizontal cracks or vertical cracks? What do you think? Vertical or horizontal cracks? In this case. Okay. Where does the restraint coming from? Let's say if I want to strain, right? Now let's say you have this wall here. This wall want to strain, right? Where is the restraint coming from? Restraint coming from here. Right? Because here this thing tries to shrink. But here this part here, because it is tied to the ground, it is not going to shrink because it's fixed to the ground. So here want to shrink, here doesn't want to shrink. So what happens? This will be under tension. This will be under compression. Understand? So when this is under tension, this will crack. Okay. So normally a wall, the cracking normally is here, not so much on the base. Understand? Understand? Okay, follow? Can understand? Okay. So that is why, and the bigger the piece, okay, let's say if you do continuous like this, right? So let's say you do like this, okay, and this one and this one, because when you do 135, so that means the adjacent are hollow, right? So then there's less restraint, okay? But the contractors would prefer this one, continuous. You want to do like this, okay? But I have seen, this is not only for the walls, but also for the slabs. Now I have seen, actually in a project, it's a factory. It's a factory actually for chemical factory. Okay, and the floor is now whenever the floor has cracks. Okay, in chemical factory, they want super flat floor. Super flat. Okay, no cracks, anything like that. Okay, they will control the cracks because a lot of these factories, they have they manufacture and then they store. And then how do they store? They use the forklift. So there will be forklift running on the ground. Okay, so you don't want the floor like that. The forklift is okay because the forklift may carry some chemical liquid or whatever. Okay. So one of the things that they do in the floor is they stagger cast, and they stagger cast. The client actually wants the stagger cast. Stagger cast meaning that, let's say this is the floor. So you cast this one, cast this one, cast this one, cast this one, cast this one. So it's staggered. So that here there's no restraint here. There's no restraint here. Then they can shrink freely. Okay. So when they can shrink freely, you will not have cracks. Okay. Alright. Okay. But just to okay, here construction joint. And then we have movement joint. A movement joint. Okay. Okay. Here, this is the wall. Okay, vertical. This is the slab, horizontal. Okay. So this is your first cast. This is your second cast. Okay. Now, because you have water there, so not only this is what they call partial contraction joints. Okay. And there is the other one is full. Partial is because this bar is running through. This bar is running through. Okay. Concrete bond broken and joint. So they break. There's no bonding. Even though the rebar runs through, but there is no bonding in the concrete. Okay. And then here they will have a sealer. Okay, so the water will not seep through. So in case the water seep through, you have the water bar. Okay, this water bar, that means the water will not directly go like this, right? If it wants to seep through, it will have to go like this. And that is not the natural path of water. Okay, and so, because why? Let's say the water, okay? Water can flow down, right? Okay, water is so easy to flow up, you know. Correct, alright? Alright, so this is water bar, very effective. Okay, very effective. So you have the center bar water bar. Okay, center bar water bar. So then over here, this is the water surface. So we have a sealer, and then over here you have a surface water bar. Okay, so these are in normal construction building. Normally you don't provide this. You don't provide this sealant and the water bar because sealant quite expensive. Okay, sealant is a chemical compound, right? Very expensive, and the water bar. Okay, so this is the liquid adjacent phase. So the code plan quite a lot of statement on these contraction joints. Then this one is a complete movement joint. Complete. You can see that this one the bar doesn't go through. Okay, the bar doesn't go through. Okay, now the bar doesn't go through. Okay, so sometimes they provide these key joints. That means they use this one to lock the concrete, even though there is no bonding there. Okay, that means you have this because it's kind of like a socket. This one is like this one is like this. So you cannot, right? So that helps you to in the shear resistance because my rebar doesn't go through. Okay, all right. So normally they have a term called shear key. This is a shear key. It required. Now, of course, normally people don't like to do shear key one because construction-wise, it's easy to form something like that, right? Rather than form something. Okay. So you have center bulk water bar. The same thing here. Here, your compression filler, sealant. Okay, and these things that doesn't go through. Of course, this complete construction joint. That means this one, if they want to string, they are free to string. Okay, because this you really don't have much of string. Yeah. So here provision of movement joint. So here this one. Just now we are looking at the joints between slab and slab and between wall and wall. What happened? We have the slab here and the wall here also. Okay, because this is flexible sealer because you don't want the water to flow through the house. Okay, all right. So the joints is the weak point of this water tank because this is where the water can seep through. So that's why we have this is what we call the joint treatment. All right. If you look at this table, there is a design options for control of thermal contraction and restraint shrinkage. Okay. Okay. We have basically three categories. One, two, three. Three categories. The third one is the most expensive one. Okay. Closed movement joints spacing for freedom of movement. Closed. That means there will be a lot of joints. Okay, there will be a lot of joints. So let's say this is the wall, very long wall. So you will have one joint here, one joint here, one joint here, right? Okay, it means very close. Okay, when you have very close spacing, of course, the joint material are expensive. Okay, and it takes more time. Okay, instead of casting it 3 times, let's say you cast it today, right? And then 2 days later you come and cast this one. 2 days later, there will be 4 or 5 days. So if you can combine this in 1 day, that will save you time. Okay, but there's a purpose for this, because the closer the movement joint, okay, the better is the temperature and shrinkage control. So what is the benefits of this one? Okay, the cost we have talked about. The cost is you have to pay more for the joints. Okay, instead of one joint here, now you have to pay 3 joints there, right? And then the time is is longer. The benefit of this is the minimum reinforcement ratio will be less. Remember, we have this rho critical for the plain bar as 0.64%, right? Or 0.35%, depending on whether you use the plain bar or you use the high yield bar. This one allows you to have smaller 2/3. Okay, the rest is minimum of R critical. Minimum of R critical. This one is minimum of 2/3 R critical. Okay. Then, if you decide to use this one, then you ask yourself, how close is my spacing? 1 meter, 2 meter, 3 meter, right? So there's a way to calculate this. Okay. So complete joints if you use complete joints, that means the rebar doesn't go through, then the spacing is less than or equal to 4.8 meter plus W divided by epsilon. 4.8 is easy to understand. W is actually the crack width, epsilon is the strength. Okay? So alternative partial and complete joints depends on the type of joints, your spacing will be different. Okay, your spacing will be different. The other extreme is continuous for full restraint. That means no joints from one end to the other. Okay, so no joints, but expansion joint where spacing may be designed on walls and roofs that are not protected from solar heat again, or where the combined liquid is subjected to. Here, conventional small bar and close spacing to avoid high steel ratios well in excess of R critical. If you use this one, okay, your reinforcement ratio to control your temperature cracking will be much higher than R critical. Okay, so you have cost and benefits. Okay, so here is a semi-continuous or partial restraint. So you have different choices, and these different choices will affect the reinforcement that you use for your horizontal reinforcement. Okay, and of course it will affect the spacing of your joints. Okay, all right. So let's go back to the examples. So now we come to this part, transverse reinforcement. Transverse reinforcement, that means in this case is the horizontal reinforcement. That means transverse to the vertical. Okay, all right. Transverse means perpendicular. Okay, transverse requires depend on jointing arrangement. Depends on your jointing arrangement. Just now I said option 1, 2, 3. Okay. If there are no structural actions in that direction, options are defined in table 11. Range from table 11.1 is the table that I just showed you. Okay. Range from continuous construction to closed joint spacing will still reduce to 2/3 of table. Okay, which is the equivalent of 10. If you use 2/3 of this one, this will be T10 at 185 millimeters in each face. Okay, that means T10 at 185, meaning that this one will be T10 at 185. If you use 2/3. Okay, understand? Okay, all right. Here, this is assuming that if you use T10 at 185, that means you are using R critical at 2/3 of the reinforcement ratio. Reinforcement ratio is equal to 2/3 of the R. Meaning you are using the option 3. Okay, option 3. If continuous construction is to be used, continuous construction that means no joints, right? Crack width including seasonal temperature change should be checked, and it will be found that a total slip area of at least 144 millimeters square per meter is required to satisfy the 0.2 millimeter. Okay. Just now I said there are option 1, 2, 3. If you use option 1, you find that you require 1440 millimeters square. If you option 3, you only use 853 millimeters square. Okay, so almost reduced by half. Okay, reinforcement reduced by half. Okay. If you use option 3, but the thing is, then you have to pay more for the joints and the time delay. Okay. Here, they decided, and this author decided to use option 3 for table 11 points adopted. So the alternatives are, there option 3, you also have 3 alternatives, 1, 2, and 1, A, B, and C. Okay, A, B, and C. So let's look at if you use option 3, that means you will provide this one already, T10 at 185. Okay, the only question is, where should my joint spacing would be? Okay, so reinforcement will be this. Okay, just 2/3. So in terms of calculating of the reinforcement, this is the easiest, right? Then the next thing is, how would your joint spacing be? So let's say we have this one, complete joints. So complete joints, the spacing would be at least, this is 4.8 meters minus W over S, W over epsilon. That means the maximum you will have is 4.8 meters and or below, because it's minus, right? Where W is the allowable crack width. So allowable crack width in this case is 0.2 millimeter. So it's 0.2 times 10 to the negative 3. Epsilon is a thermal strain. Thermal strain is, this is thermal coefficient, right? Thermal alpha C is a complete thermal coefficient. Thermal strain depends on how much temperature there is. Okay, So in this case, T1 is 23 degree. Okay, thermal strain is, which is a concrete property, is 10 times 10 to the negative 6. So normally strain is very small one. It's 10 to the power of negative something. 3, negative 4, negative 5. In this case, negative 6. Okay. So, and this one comes up to be, the strain is 115 times 10 to the negative 6. So the spacing must be less than 4.8. 4.8 plus this part, plus, okay. So at least 4.8, at least 4.8. So plus this one, so this is 0.2 times 10 to the negative 3, and this one 115 times 10 to the negative 6, right? So this will give an additional 1.74 meters. So the total is 6.54 meters. That means your spacing is 6.54 meters. Okay. Now 6.54 meters actually is quite short. Okay, it's actually quite short. Okay. So here is, this one is 6.4 meter is full movement joint. Full movement joint. This one is, let's say, partial joints. Partial joints, that means, okay, partial joint be less than or equal to S max plus W epsilon. Okay. Now S max is, I think in option 2 they calculate the S max already. In calculation explain the steel area. So the S max is correspond to the steel area. S max, the formula is this. S max is, the formula is this one. Okay, this is FT, FB. This is the bar diameter 2 times. This is the reinforcement ratio. Okay, so that is that formula, and in this case, so in this calculation, S max may correspond to a steel area of 853 millimeter square per meter and 10 millimeter bars. So when you use the S max calculation, the rebar you use 10, okay, and the reinforcement ratio you use 853 millimeter square per meter. Okay, so what would be the reinforcement ratio? Reinforcement with 853 millimeter square divided by the concrete area will be 1 meter and 200 millimeter. Okay. So option 2, the spacing is 4.73. Option 3, the spacing is 2.91. Okay, it means this one is even closer. This one is less close. This one is further apart. Okay. Now why is it that? Because as you allow it to string freely, it means you can actually have a wider, longer spacing as compared to where you have the restraint. Okay, let's say if you have the restraint partial joints, okay, you see that this is 3 meters. Every 3 meters you have to do one. So if it is a 30 meters, that means you have to do 10 panels. Okay. Okay, so that's about it for the water tank design. Okay. Right.
How we know we need to use the T10 and then 1, 4, 5 spacing? How
Which
we
one?
know we need to use T10 and 1 and 5 spacing?
Oh, because here they say that, let's say if you choose option 3, that means you are going to provide closed joints. You want to provide closed joints. Then you can use a reinforcement ratio which is 2/3 of the cradle. Because you have, that means before you ask yourself, oh, should I use option 1, 2, and 3? Option 1 is fully continuous. right? No joints. Okay. Option 2 is, I think, semi-continuous with joints. Option 3 is close spacing. Close, I think, what they, if you look back at the option that they have, here, option 1 is continuous for full restraint. Okay. The other extreme is close movement joint spacing for freedom of movement. Okay. This is practically full restraint. This is kind of like no restraint, right? This one here is semi-continuous or partial restraint. Okay. So here, if you choose this one, your reinforcement will be more. That means the horizontal reinforcement will be more. How much more you have to calculate that one based on the S-max, and that means basically you have to calculate the crack width. Your reinforcement that you provide have to make sure that the crack width is less than the allowable. Okay, so you start. We may start. Let's say you, let's say your crack width. Let's say your crack width is less than 0.2 millimeters. This crack width is due to the temperature and shrinkage crack, right? So how do you calculate the temperature and shrinkage crack? So this one is equal to what? Equal to S max multiplied by, and then multiplied by T. Okay. So this we know this is 10 times 10 to the negative 6. Temperature, yeah, because that is the concrete properties. That is the thermal coefficient. Thermal coefficient. Okay. Thermal coefficient, that means actually is a thermal strength. That means 1 degree of Celsius. Okay, 1 degree of Celsius. What is the strength? What is the shrinkage strength or the expansion strength? That is the material property. So that doesn't change. Okay. T is the temperature. That means from your peak temperature, okay, your peak temperature hydration to your ambient temperature. Okay, it could be different countries will be different. Okay, different countries will be different. So and even the same country, let's say if you do the concreting in the summer and versus the concreting in the fall, the temperature change will also different. Okay, all right. Because the ambient temperature is different. Let's say in the summer, your ambient temperature may be 30 degrees Celsius. In the fall, maybe it drops to 23 degrees Celsius. Okay, so your peak, so your difference in temperature will be different. Then the other thing is S-max. So this S-max, just now I said S-max is calculated based on Ft over Fb and diameter divided by 2r. Okay, this is tensile strength. Bond strength is also basically determined. Okay, I think it's 1.6 MPa. Those sort of things. So this here depends on your bar diameter and then your reinforcement ratio. So you set up these equations. So what you have to do is you set up this equation Ft over Fb diameter 2r, then multiplied by alpha 2 multiplied by T, and this has to be less than 0.2 meter. And then you solve for this reinforcement ratio. Okay, so that is how, if you look at the examples, they tell you that if you use this option, you require, I think, 1448, right? How did you come up with this one like this? It just didn't tell you. You see what I'm saying? So let's say we go back there. You say that
if continuous construction is to be used, crack width including seasonal temperature change should be checked, and it will be found that a total steel area of at least 1440 millimeter square per meter is required to satisfy the 0.2 millimeter limit. So they tell you verbally, they didn't tell you how they get it. How they get it? Okay. They solve this equation for the reinforcement ratio, and then convert it back to the millimeter square.
The R we calculated for
R is the ratio, reinforcement ratio.
R critical.
Huh?
R critical.
Huh?
R critical.
No. R critical and R are different. R critical for plain bars is 0.64%. Your R has to be greater than this one. So in other words, whatever you calculate here, you have to compare with this one. If let's say this is less than this, then you have to at least provide 0.64%. And if this one is more than that, then it will be okay. That's what I'm saying. Alright. So here is 1440 millimeter square per meter. This one, if you convert it to the R, it will be more than the 0.64%. Okay. Right. So what they tell you is option 1, you will use this reinforcement. Now, if you don't want to use this, you want to cut down on the reinforcement, then you can use option 3. Okay. So option 3 will be less. Okay. Option 3 you use 353 millimeter square. Okay. But then option 3, it involves a movement joint. Then you have to calculate what is the spacing of the movement joint. If you option 3 reinforcement, you don't need to calculate that much. It's just 2/3 of R critical. Okay. But the thing is, because option 3, that means you are using close spacing of joints, right? Then you have to work out how close is your spacing. Then you have to tell people. Okay. Option 1 is no spacing from end to finish. Option 3 is you have intermediate spacing, right? Then you have to tell people, hey, how intermediate spacing, what is your spacing? Okay?
The epsilon for the option 3.
Huh?
Epsilon.
This epsilon here. Epsilon here is the thermal strain. The thermal strain. Thermal strain is just thermal coefficient multiplied by the temperature.
Temperature will change a lot based on
Temperature, as I said, temperature is, they have, in this table, they have the temperature. Typical design value of T1 for PC concrete in the UK. Okay, so it's given in the BS A110, right? So this one depends on your thickness, wall thickness, depends on your cement content, depends on what kind of, I think it's in the code also. But the thing is, you need to be careful. No, it's 8007, right? Can you find the table? This one. Right, it's the same table as that. The table 8.2 is in appendix. It's in appendix. You guys have the. Now, let's say this is T1. T1 is what? That means the peak temperature, the peak hydration temperature. So when you pour the concrete, as the hydration process progress, your temperature is going to increase, right? So you increase up to a certain level, then of course it starts to cool off again, cool off to the ambient temperature, right? So that difference is the T1. Okay. All right. Now, okay, why don't you guys spend a bit of time looking at this? I'll come back and explain a little bit more on this one.